Section 12.6, part 2, I just want to make a comment about this graph, which I did, and I kind of waved my hand, and lo and behold, I got this rough sketch, and I never showed you how to graph these hyperbolas. So if you don't mind, let me just show you accurately how to graph those hyperbolas, just you know how it's done. So keep in mind, these guys are what? This is like an ellipse. Okay, these are hyperbolas because they have a minus between these square terms, hyperbolas. These are curves. These are the curves or cross-section of the surface with what? XZ plane and YZ plane. There it is. Suppose I want to graph this hyperbola. So what do? I go 3 units along the what? X-axis, because if you set y equal to 0, x is plus or minus 3, like so. Then if I set what? You kind of set each of these numerators equal to their denominators. That's basically what it amounts to. So if I set z squared equal to 25, I get z is equal to what? Plus or minus what? 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, like so. So now you make a box, auxiliary box, that's what it's called. So from the z-axis, you kind of draw what? Line parallel to the what? X-axis. And from here, you draw a line parallel to the what? Z-axis. So lo and behold, you get this auxiliary box. So what's so good about auxiliary box? If you connect the diagonals of this so-called auxiliary box, that would be called asymptotes of the hyperbola, correct? And because x showed up first, so the branches of the hyperbola opens up along the x-axis at -3 and 3 for x. So you kind of go like this. Do you see it? Okay, so there, that's portion of it. For this guy, you have what? Y squared over 4 minus z squared over 25 equals 0. That's like by setting x equal to 0. This is like by setting y equal to 0, correct? These are the cross sections of the surface by what? XY plane, XZ plane, and YZ plane. This guy is also a hyperbola because there is a minus between the square terms. So now you have what? If you set the numerators equal to their own denominators, so you get plus or minus 2 for what? Y, correct? And for z, you still get what? 5 and -5. Now from here, you kind of what? Graph a line, what? Parallel to the what? Y-axis. And from these two points, namely plus or minus 2 for y, you graph parallel lines to the what? Z-axis. Now, connect the diagonals of this guy to this box, which is called auxiliary box. And because y has showed up first, so what you do at these 2 points, you kind of what? Graph one more hyperbola, like so. Do you see it? Make sure the hyperbola, the branches of hyperbola, what? Gets closer and closer to the asymptotes. That's what these guys are called, asymptotes, correct? So those are called asymptotes. There you go, which means guidelines. Is that right? So now, remember, at z is equal to plus or minus 6, okay, so if you replace the z in the original equation with plus or minus 6, just to see what the cross-section of the surface with what? These 2 planes, you know, they are parallel to the floor look like, it turns out the graph, the equation comes up to this guy, which is an ellipse because you have a plus sign between 2 square terms. So what's happening is you get what? an ellipse here, correct? Like so. And an ellipse here, like so. Is that right? And lo and behold, we have hyperboloid of one sheet. Now you see how these branches come about by simply graphing what these hyperbolas. So with that in mind, I'd like to now go over quickly over this handout, and then we should be A-okay. So if you really want to see a fancy graph of these quadric surfaces, let me just zoom in. This is how they look like. This is how ellipsoid looks like. This is a cone. This is elliptic paraboloid, which is like a cone, bowl. This is like a hyperboloid of one sheet. Remember, it looks like a nuclear plant. This is like a saddle. And this guy is hyperboloid of two sheets. So the question is, now that we know a little bit about what these quadric surfaces, is there any way we can identify these, what, 8 so-called equations? And if so, what would be the name of the surfaces? Okay, so what we got is the following. The first guy, as you can tell, you can write this as x squared over 1, correct? Let me just change my pen here. X squared over 1. Did you know you can write this as y squared over 1 over 4 plus z squared over 1 over 9 is equal to 1. That pretty much matches this format. So I would say this guy is an ellipsoid. Ellipsoid. Okay, make sure you know how to pronounce it and spell it correctly. You got a bunch of squares, but one of the terms has a minus sign in between, so that must be hyperboloid of one sheet. Notice these are plus, plus, and a minus, and you have squares. So this would be hyperboloid of one sheet, correct? And by the way, because y has a -1, so the hyperboloid of one sheet opens up along the what? Y-axis, correct? This guy has squares. All three variables have squares, but two of these guys have a negative. So that would be like what? Hyperboloid of two sheets. So this guy would be hyperboloid of two sheets, okay? And because y has a positive sign, so the what? The sheets open up along the what? Once again, y-axis, correct? So this is one sheet and this is the other sheet. Y is equal to 2x squared plus y squared, kind of falls into this category. So this would be elliptic, what? Elliptic paraboloid. And because you have y, not z, so the bowl or the elliptic paraboloid opens along the what? Y-axis. Do you see it? Like so. Y squared equals x squared plus 2z squared. That falls into this category. You have positive squares. One of the terms, square terms, is on the opposite side of the equal sign. So definitely this is a cone. And because y squared is on one side, therefore what? The cone pretty much lies along the y-axis. Y is equal to x squared minus z squared. That's kind of like a saddle, which is also known as hyperbolic paraboloid. So this guy was a cone and this guy was a saddle. What is this? Well, if you were to square both sides, you would get this. That's kind of like a cone, right? But remember, we're only taking positive square root. So this would be like what? Upper half of a cone, correct? It's the upper half. What is this? Well, if I had z is equal to x squared plus y squared, that would be this graph. elliptic paraboloid. So you would get this. Is that right? But I have negative, okay, guess what? That just makes your what? Bowl to open what? Upside down, correct? So excuse me guys, a bowl. Is that right? And the one here, just moves this upside down elliptic paraboloid 1 unit up. So z is equal to 1 minus x squared minus y squared. It kind of looks like this, folks. You see it. Make sure it doesn't look like a cone. It's an elliptic paraboloid. It looks like a parabola, not a cone, correct? Finally, this is how I got these pictures using a program called Mathematica. Okay, the free version of this program is called Wolfram Alpha. You can just Google it and you can graph these on that site. So this is how elliptic paraboloid looks like using that program. Here is the cone. Here is the hyperbolic paraboloid, which is like a saddle. Here is like a what? Ellipsoid, which is like a football. Hyperboloid of one sheet and hyperboloid of two sheets. So I kind of, input the commands, and this is how the program came up with these pictures. Thank you.